So the slides are up here, and I'm very happy to present today. Thanks for the introduction, Kiel. When we talk about intelligent systems, when I looked at the program and past presentations from the past years, just wanted to put in perspective what we at Cadence look at intelligent systems and how Cadence fits into the whole picture. When we think about intelligent systems, it's really about what I would refer to as really ubiquitous hyperconnectivity. You have sensors, you have devices like our phones, you have local base stations. So those are the elements you drive by on the highway and you see those radar antennas. You see sometimes you don't see it that much within a stadium, for example. So think of Wembley having a local environment and a local setting there. Then data gets accumulated locally within certain metro areas. So you have local aggregation. And from here, you have what we would call local data centers. And eventually, we have the cloud as it is doing all the data processing. So you really have this hyperconnectivity across that, and the circles imply the different areas of compute. So you have discussed during the conference already yesterday and will in the final sessions the whole notion of edge computing, where edge is always measured as distant from the data center. So you have near edges and then your device edge and your sensor edge. And the big question Cadence is involved in enabling all this from a chip and system perspective is, where does the compute happen and what do you do with all the data across that whole ecosystem of hyper-connected devices? So the application domains Cadence is targeting as end industries span these 8, from hyperscale computing itself through consumer, mobile, networking, aerospace, defense, automotive, industrial, and health. Those are just some of the applications in which hyperconnectivity and hyperscale computing plays. And it's just a very exciting environment and a driver for electronics overall. Here's just some data about the growth of this domain, where the global data sphere, according to IDS, is really growing to about 175 zettabyte. You have the creation from sensors, these intelligent small systems like my Fitbit or any health tracker or any other tracking environments you might use. And the sensors in an industrial environment, they have phenomenal growth ahead and predicted. And just the amount of data transmitted through networks per month is just significant. Just to put this in perspective, this is like for the reception we'll hopefully have next year, some small talk and some knowledge to have how much data is actually in a zettabyte. I had to explain this to my family the other day. Well, it's as much information as there are grains of sand on all the world's beaches. So next time somebody asks you, what the hell is a zettabyte? It's quite a bit. It's a lot of data, lots of zeros. And it's really for electronics, and Cadence being a player in the electronics market, it's a once in a lifetime opportunity. We're looking in 2025 at about 2.9 trillion of systems in the OEM environment, like all the phones, all the computers, all the devices sold, which is fueled by predicted to be well over 500 billion semiconductor market. And then Cadence, in case you haven't heard of us, we are one of the top 3 players here in this electronic design automation market for chip development, which is part of this $80 billion tool enablement market, which spans from electronics tool environment through mechanical tool and all the multi-physics domain simulation. And we are coming from the EDA world, the chip design world, and we have been growing over the past decade significantly in the systems enablement world as well. So how does EDA do this? What is the environment we play in here? Well, there is really this flow from building blocks all the way to system integration, where you select building blocks. So one of the building blocks you might think of and know of are things like the ARM processor cores. ARM is the biggest IP provider out there for semiconductor IP out of Cambridge, UK. Cadence, for instance, is providing building block IP for interfaces like PCI Express. We also have a digital signal processing a core environment called Tensilica. You put this together, you verify hardware and software, you build the chip implementation with custom and digital custom analog and digital implementation. You package it into PCBs, and it becomes then a part of the system analysis when you put everything together into your systems. And Cadence is very much involved in enabling AI and ML, artificial intelligence, machine learning chips and systems for users to build them in a semiconductor and system environment. So that's one area where Cadence plays into this market, and there's a very significant number of startups and companies around building these chips and systems today. Just a brief refresher, as you guys have probably had all of this in school, what we mean by chip design. It's really going from hardware description languages into the physical layout of a chip, which is then manufactured in a silicon technology. There's IP reuse going on, with a lot of software having to be put together with the hardware. And then you have flows for digital implementation and custom analog implementation, going from schematics to the layout, and from the higher level description using synthesis to layout, and then from there into manufacturing. And the focus of the next 20 minutes here is really how is Cadence using artificial intelligence and machine learning to increase the productivity of our flow. So not only enabling the chip and system development in the electronics industry, but using AI ML for our own tools internally to make you as an end user, the developers, more productive using our flow. So AI ML has helped with the tool development there quite a bit in recent years. And to give you an impression what happened over the last 40, 50, 60 years or so, we started originally with layout being done manually. That was abstracted to circuit simulation at the transistor level. When that became too complex, we did do gates. That's when I started myself doing chip design back in the late 80s, early 90s, doing chips for HDTV development. We abstracted at the time in the 90s to language-based description. So that's where Verilog and VHDL came in as descriptions for hardware. In the 2000s, this became platform-based design, where you had predefined platforms. In the 2010s, we had, over the last decade, multi-core has become a big issue to deal with software and hardware partitioning across multiple cores. And in automation, EDA, we have been really, for the last 6-7 decades, been very much involved in automating this flow. And the way this flow automation always worked in the past is that we would abstract the lower level of abstraction into a model at the next level. So that's very familiar for everybody dealing with AI ML. There's a lot of modeling going on. Then at the next higher level of abstraction, you simulate everything. So you will take your Verilog VHDL, for instance, and in the 70s it was the transistor circuit simulation. You simulate that, and then you automate the implementation to the next further down abstraction layer, using the results of the simulation, analyzing and optimizing this flow. And this has been happening for a significant amount of time, increasing productivity. And we have just entered, and this is some of the pioneers in this whole domain, John Hennessy and David Patterson, in their Turing Award lecture a couple of years back, they talked about this golden age of semiconductor, where we now, as a next step here, really look at domain specificity. We look at very domain-specific architectures, domain-specific languages, and do hardware-software co-optimization. And in this context, the technology aspects we are working on automating here in the 2020s is this notion of heterogeneous integration of chiplets, where you no longer put everything onto a system on chip, an SoC, which you may have heard of, but now do a lot of chip development in using a disaggregated environment with heterogeneous integration. So that's the next step of complexity which our industry is working on, and it really becomes a multi-physics situation where you have to have the different silicon components from different technologies, and you have to analyze the electromagnetic, the thermal, and the mechanical effects, how you put all that together. So that's where you may have heard Moore's law coming to an end. That's really what we refer to as more than Moore, where you really integrate this now at a disaggregated level. For AI ML, the areas we at Cadence target are really what we would refer to high effort aspects of the design flow. And here's a chart coming from IBS, and we work with them on this, where you see the efforts. And the dark blue portion here is the implementation of layout. That's where, and the chip where we'll talk a bit more. The light blue here is verification, and the greenish parts are the software. So those are the high effort components for chip development, and then extending from there into system development. That's what we are focusing on for AI ML in EDA, and taking this model of capturing data, abstracting to a model, simulating, analyzing, optimizing, and then automating further down. Taking this, if you translate this into how machine learning and artificial intelligence are used in this context, you have a lot of data collection in the capture phase. You have neural networks that are getting trained. This training is typically done using simulation. So that's this part up here, where you create terabytes of data in very short time, doing a lot of training of these networks, and then there's reinforcement training going on in that level. And the same is true when you then look at different implementation options. So that's the architecture component, looking at the different implementation options, and then learning essentially from the implementation how to improve it. And we are working here towards more and more autonomous operations, always controlled by developers, but this flow is becoming more and more automated. So you can think of this as the different levels of autonomy which you find in a car autonomous driving environment. So to give you a glimpse of the complexity we are talking about here, you have seen all these examples, and we were all very excited and thoughtful when we had the cases when chess grandmasters were beaten the first time, and the best Go players were beaten the first time by machine learning and artificial intelligence trained networks. To give you an impression of the complexity of the number of states, chip placement alone, and this is just the placement of the components on the silicon estate you're dealing with, is already an order of magnitude here bigger than the number of states you have in Go. And not only is the state space for that already bigger, this is in reference here from recent articles from Google, I've referenced down here, this is not only the number of states for the placement here, which is much more complex, but you also are facing a situation where it's not a win or lose like it is in chess and Go. You're actually trying constantly to balance various parameters, and especially the bold ones here. PPA is a term you hear quite a bit: power, performance, and area, translating into cost. You're constantly trying to balance the implementation based on those parameters, and then take into account the software, different architecture options, and the whole more than more implementation options. So the state space is unimaginably big, if you will. So this is not in comparison with Go and others, this is not an easy problem to deal with. And if you look at machine learning in electronic design automation today, you have design data as an input. For instance, the Verilog VHDL describing the hardware and the software description in C++ mapped onto it. And you put it into your algorithm, and you define the objectives. I want to have a certain power envelope. I have a certain cost I need to meet. We differentiate between two different types of machine learning here. One is what we refer to as machine learning inside, where you have the cost functions within the tool captured in a neural network, for instance, and then that neural network becomes the cost function. It's largely invisible to the user. It's in effect becoming a increased productivity that the user sees, but the user may or may not be aware that actually a trained neural network is doing that and it's supporting that within the algorithm. So that's hidden from the user, if you will. That's what we refer to as ML inside. And then there is this process we refer to as machine learning outside, which is in a sense capturing the experience and the knowledge and the ideas which a designer puts into operating the tool. So here we are looking at tool options, preferences, constraints, and I'll give examples of all of this in the remaining 10 minutes here of how EDA is dealing with that. So that's the ML outside portion, in a sense capturing and learning from the experience of a designer how to operate the tools. I will not be able to go into all opportunities in electronic design automation and system development where AI ML is applied. I'll talk much more about the verification portion and the digital implementation portion in the remaining 10 minutes. There are many more opportunities here for applying AI ML, and we are looking forward as Cadence working with you, the research and experts community, on ideas how to exchange thoughts there and how to look at different disciplines, how AI ML is used there. But we are, for example, characterizing the technology libraries. We are dealing with yield in the area of design for manufacturing, trying to get the best yields from silicon implementation, all the way to optimizing the system analysis when you put together the system. So let's go through two examples in the flow. The first one being the digital implementation. And the digital implementation is, if you look into a design flow, this is a timeline which is roughly following the efforts and the timelines of chip development, where you go to what we call a tape out, where you give it to fabrication and you get the silicon back. There's this very large spot in the center where you do the implementation of the environment and the implementation of the chip. And that's where you go from, in a digital world, from a description language like Verilog to the layout and then the GDS2 with the different phases like the gate level in between. And there are really two pieces here. There is the inside, ML inside portion I mentioned earlier, which is dealing with the prediction of delays. And then we have just recently come out, and you have seen potentially things in the press over the last couple of months here, with what we refer to as Intelligent Chip Explorer, which is the ML outside flow optimization of the implementation. So let's dive into some details of this today. The first one being ML inside. One of the items when you look into the layout from an initial design here, as you're laying it out in a silicon technology, let's say a TSMC technology, 7 nanometer, or a global foundry technologies, you have different options there. You essentially look at the layout implementation, you model the delays, and you train a neural network to predict the actual results from the model inputs. And then you apply that for the implementation, for predicting the delays within the semiconductor implementation layout. And that's really getting you improved design performance. And here are some examples from various technology node, 12 nanometer down to 5 nanometer, where you look at things like the total negative slack and the power consumption. And with this model, which is largely hidden because it's inside from the user, the tool learns as you are doing more and more layout, the delay prediction and how to predict it, and improves the placement and with that the implementation. The second portion I had mentioned is this notion of ML outside, where we're essentially capturing the user's experience, the developer's experience, and assist the developer to become more efficient. So here's the engineering effort, and here's what I had mentioned earlier, PPA, power performance and area, or power performance cost. And the way this works today, you start with a development based on the designer's experience. You invest more effort. You kick off different implementation options. The tools are running through synthesis and the placement and the timing and layout prediction and so forth, and going through options. And it's a manual effort to do this and to develop those, to get this information. It takes significant time, and it's really based on user guidance. The objective now is to improve the cost, and to do that faster, use essentially more CPU time, use trained networks over time with better implementation, and really reduce this effort spent and get better performance, power and area out of it. Go through these options, which I had mentioned earlier with the example of Go. And that's what we have introduced a while back with something we refer to as Cerebrus, which is essentially a tool environment in which you take the design input, you run through your flow, and as it comes through different results, you train with reinforcement learning a neural network, really taking the designer's variation of the different options and so forth, and learning what the best results are, and doing it in a parallel environment. So the cloud comes in handy here, improving the performance, power, and area. And here's an example of a 5 nanometer CPU where we actually were able to improve the performance, the leakage power, the total power quite significantly using this flow. And it's really gated by the variations a user gives the tool to look at and really optimize for, and the amount of parallel executions you allow the tool to use, the amount of resources you allow it to use. In the phase of the floor plan, where you basically put down the different building blocks of your design, Cerebrus also is using the mixed placing technology here to optimize the speed in this particular case by learning the best layout, to basically folding and looking into resizing into various directions, and by using this and then training the network to learn in which direction to explore further. you get the implementation optimizations I've mentioned here on the right-hand side. There are several customers. Here's an example from Renesas where they basically got, it's a flow optimization, much higher throughput for their product development. So that's number one. Number two, the example I want to use in the last 5 minutes here is functional verification. So that's the other portion in the development graph where you really verify that your function is correct. This is the implementation I just talked about. Here it's the simulation to verify correctness and to verify the functionality. And that's actually taking into account a lot of the green bits up here of the software as well. So it's a very complex simulation environment, takes significant effort and time throughout the development flow. And what you do in this domain, there is a set of dynamic simulations. You kick off a lot of regressions during the flow, a lot of simulations where you run these simulations over time. And where AI ML is used to optimize this is really with the regression handling here, looking at the best way to sort and the best way to direct with directed testing, the exploration, the simulation. And we're really using the AI ML environment to train neural networks to understand how to get to the same coverage, so the same coverage, functional coverage of the design in shorter time by optimizing the regressions appropriately. So it's really about verification throughput, reducing simulation cycles, and essentially avoiding cycles which don't add much to our design objectives for the simulation, getting matching coverage through proper randomization of the test suite. So the AI ML really learns how to reduce the CPU cycles while maintaining, as shown on the right side here, the coverage results with shorter simulation time. Again, an example here from Kioxia. They confirmed, in this case, 4 times shorter turnaround time to reach 99% of the same functional coverage of the original. So very exciting space, and a lot more can be done in that space as well for optimization. Another part of verification is what we refer to as formal verification. That is formally proving the properties of a design. And what you do there today, you have SAT solvers and you have all kinds of very advanced formal verification engines. You kick these off in parallel and you then basically orchestrate how much resources you are providing for each of those solvers. And we are training essentially within Cadence a neural network to understand how to orchestrate this better and how to learn which jobs to switch off and basically save resources with this trained network, which we actually train within Cadence, and then you get a pre-trained network as part of the product, which allows you to get to closure faster and to basically get to more closed properties, going back to the previous slide here, more determined properties and shorter amount of time. So these curves get steeper. Again, an example here from Europe. StMicroelectronics was one of our partners. We helped working through this. They got faster regression and reduced the number of non-converging properties significantly. So in summary, these are just 2 exciting examples from the functional verification domain, the digital implementation domain. But as I indicated, the flow is very complex, and there are many other areas where AI ML helps to train to make our products, to train neural networks to make our products more productive for you, the users. So for example, we found for the library development acceleration potential by interpolating libraries with getting almost the same pass rate. There's a lot of work going on in the board design, the printed circuit board design, with getting to faster design closure and routability. And essentially a lot of the optimization we get from neural networks is to allow to reduce the simulation time and really use the high value execution of simulation cycles. And that extends from functional verification, which I had talked about in a little bit more detail, to all the way to the system design tools where you can optimize sweeps. So this is truly just the beginning. So the vision which Professor Hennessy and Patterson had outlined in their Turing lecture about this golden age of compute and semiconductor with domain specificity, where you have much more targeted, specified workloads, is enabled by the increased productivity of our tool. It's really just the beginning, and we're at Cadence really involved closely in this convergence here of system design, the classic IP reuse and electronic design automation with the AI ML and data analytics, really coming from the chip design to the system design towards what we refer to as pervasive intelligence throughout, enabling and using AI ML for better flows. And this is just the last 60 years where we went from the original invention of the transistors and initial manual implementation of EDA enabling all this, where we are now from edge to cloud, 5G, we're talking about 6G, specialized SoCs, artificial intelligence, chips and systems enabled by these development flows we at Cadence are very involved in, with parallel and distributed compute solutions like the implementation flow and the verification flow I showed earlier, which are really a full flow, if you will, and then deep learning to optimize all that. So it's extremely exciting times for electronics and in EDA.